Hi everyone. This video is designed to help you get your data for the Impulse and Momentum Lab. We're going to use our IO Lab device. We're going to need either a deck of cards or a cell phone, something about this size and weight, a small plastic bag of coins, and a nice solid book with a soft spine. Okay, so before we really begin doing anything, we need to make sure that we always calibrate our iLab device. So turn your iLab device on, power switch on the front, go to settings, which is this little cog wheel, go to calibration, and make sure you do acceleration and force. They're super easy, it'll walk you through it, no big deal. For the first part of this, we need to determine the mass of our device. And we don't have a scale. I'm assuming you don't have a scale at home to be able to weigh this accurately, at least. So what we're going to do is put the eye bolt in, the little round bolt with a screw on it. Insert that in the back of the device. Make sure that you don't cross thread it. It doesn't need to be tight. It just needs to be snug enough that it's not going to fall off if you're holding it. Now, with our device on, go ahead and go to your force. This graph will come up. One thing I want to note before we do anything, the sample rate of 4,800 Hertz, when only the force gauge is on, or force sensor is on, this thing samples at a rate of 400 or 4,800 data points per second. We need to know that for our error analysis. We're going to need to know the number of data points. You're going to multiply that number by your interval, your time interval. So however many data points it takes per second, if the time interval was 1 second, it would take that many. 4,800 per second times 1 second is 4,800. If we took a 2-second interval, it would be 2 seconds times that, and we get 9,600 data points. Easy enough. We'll go through that in the data table section of the lab, but just note that this will change later on. So for now, when we're doing our mass, it's 4,800. Now, before I do anything, what I'm trying to do is this thing has a force sensor that when I hold onto this eye bolt, it measures how much pull, how much force is being put on this eye bolt. So when I'm hanging it upside down, the whole weight of the device is on it. That weight is equal to mg. So whatever force this thing tells me, if I divide by g, I get the mass of the device. So first of all, let's hit record. And we see that it's about 0 because it's calibrated. All right. If I hold it by the eye bolt and let it stabilize, right? After a few seconds, stop it. I can see that if I take my bar graph tool, my data analysis tool, and use about a second, this is more like 1.5 seconds maybe. It says it's 2 seconds. The time interval is up here. This mu is your mean. This little phi or omega, I always forget which one that is. This is your standard deviation. Okay, and you need to write down your standard deviation. That's a measure of your error, so we're going to use it in our error analysis. It's actually a measure of like your residuals, but we'll talk about that in the error analysis. Make sure you get your mean and note that it's negative. Why is it negative? Well, because the force is down due to gravity. And this device knows that up is positive y. So make sure you get your sample rate, your time interval, your mean or mu, and your standard deviation, okay? If I take this 2 newtons and I divide it by 9.8, I get the mass of my device. So 2.005 divided by 9.81, this is 0.2044. So about 204.4 grams is what my IO device weighs. All right, we're going to assume that that is the true value of the mass. That's not to say that if we didn't do this experiment a couple times, we might not get other values. We shouldn't, but who knows? However, we're going to assume that that is our true mass of our IO lab device. Don't take this off. So next up, in our experiment, we're going to have to add mass to our iLab device. And I'm going to do that using a phone and a bag of coins. I need the mass of those as well. And if you don't have a way, if your phone doesn't have a phone case like mine, I can actually just kind of wedge that eye bolt into my phone case and it will hold it. If you can't do that, use a really thin floss or string or something, some way of suspending it from that eye bolt that doesn't add any appreciable mass. Hit record. I can see that my phone is a little bit less than 2 newtons. Let it run for a little bit. Don't shake it around. Stop it. Again, select about a second. Note the hertz, note the delta t, note the mean, and note the standard deviation. Finally, for my bag of coins, I also need that mouse. What I would do is just twist one end of the bag up, run it through your eye bolt, and it'll hold there for a second, long enough to get a mass. Hit reset, hit record, let it go for a few seconds, hit stop, highlight the data, and you can see that this mean is about 0.793. Delta t is 1.5 seconds, and my standard deviation is 0.015, and my hertz are 4,800. So now I have, if I divide this mu by g, I have the mass of the coins, I have the mass of my phone, and I have the mass of my iLab device, which is what I want. I want those values for later in the experiment. Now, if you hit reset twice, it turns off all of the sensors. Remove the eye bolt. Be careful not to damage your iLab. These things are kind of fragile. The spring with the screw on it, now I want you to insert that where the force gauge was. Now I have my 2nd edition Halliday and Resnick, which is our book that we're using now, except we're using the 10th edition. I found this. It has a really nice soft spine that I'm going to use as a wall. I'm going to roll my iLab. It's going to bounce against it and come back the other way. And this will be my impulse. From the time the spring touches the book until the time that the spring leaves the book, that impulse is going to result in the change of momentum in my cart, which is going to change its velocity from heading to the left for me to heading to the right. And that's what I want to measure. So make sure that when you roll it at the book, you don't roll it too fast so that you end up breaking this thing. Just give it a nice motion. You might want to use a lot more room. I found that if I'm about 3 feet apart, it works a lot better than if I'm a foot apart. But for the purposes of showing you how to collect your data, I'm going to do it right here on the tabletop. So turn on your wheel and turn on your force gauge. Before I turn on the force gauge, note that these are all sampling at 100 hertz, 100 data points a second. When I turn on the force gauge, notice the force gauge sample rate has changed. When the wheels are on, the force gauge only reads 200 hertz. If I turn the wheels off, it jumps back to 4,800 hertz, 4,800 data points a second. So note that when we're doing all of the velocity data and all of the force and time data here in the collisions, our sample rate for our force went down to only 200 hertz. That's important for our error analysis again. So in our first experiment, no wait, nothing, just take the cart, make sure it's on, hit record, give it a nice gentle push, let it slide, it comes back, and stop. And we can see here, actually I want to use my zoom tool before I do that. If I double click with my zoom tool on, it kind of automatically fits my graph to my screen, to my, the size, it fits my data to my window, basically. Now, what are these graphs? This is the force graph. This is the force that occurred on this spring while on the force sensor during the collision. This is my position. I notice that heading to the left is negative, heading to the right is positive. So as I started to push it right here, it went negative and then it came back positive after it bounced off the wall. This is the point where it changed and headed back the other way. As I can see here, this is my velocity change. We can ignore everything before this on the graph. But this is my velocity before. It doesn't look relatively constant. If I zoom out, it does, but since I'm so zoomed in, it looks like it was sharply rising. This is my velocity after. And this peak is my acceleration, which matches the peak of the force. However, I would use this acceleration as a measure of your impulse when you choose your duration for the impulse, because the force sometimes is really noisy. So what I mean is, the first thing that we want is we want to go around the force. And I could really actually zoom in here and make sure that I'm really getting it. When I zoom in though, just note that if I were to go here, I don't know quite where this force really ends, and that's not good enough. So what I want to do is I want to use the acceleration. And I could come down here and kind of, that's the duration of my impulse. I might want to, try and get it a little bit, but do your best. Try and get that whole force peak caught in your acceleration. So before I do that, so take the interval around the spike due to your acceleration at the moment of collision. We can see that we've caught it pretty good. Our duration starts as the velocity begins to change, and it's centered on where our position changes. And we've got our whole spike here. So now looking at this, remember your force is 200 Hertz sample rate. That means 200 data points per second. Your delta T, your mean, and your standard deviation. You want to make sure you write down all of those things, okay? So get all those things written down, because we want to know the force times the time. So from this, we're going to multiply our mean times our time interval, and that'll give us our impulse. But we need to know the error associated with that. And so we need to know how many data points we have, and that comes from the sample rate times the time interval. The next thing that you want is you want to go here, and let's go back to Zoom and select this. Pick your some time where the velocity is basically constant before the impulse begins. So I've chosen this region. Note that this velocity is negative. The mean value is negative, as it should be. It was heading left. Note the time interval, note the standard deviation, note the sample rate. You need all four of those in order to do your error analysis and your computations actually. So this velocity is our velocity before. Go for your velocity after. I find it's easiest to just pick, start right where the acceleration ends. Any interval I choose on one graph shows up on all of them, so you can get your interval for the velocity graph and see where to start it looking at the acceleration graph. I would go, I don't know, a good second, maybe a little longer. As long as the data is fairly neat, you don't want any jagged peaks. Again, mean value, change of T, standard deviation, and make sure you get the Hertz. Honestly, what I would do is I would take a screen grab. So all good, hit reset. Now we're gonna do the phone. And what I would do is set your phone or your deck of cards so that it's wedged against that felt. So I'm gonna set it here. I'm going to start. I believe if you're not getting anything, that means your power turned off. It's got a power save feature. So if your power turns off, turn it back on, hit record, give it a nice soft push. Hopefully you get some decent data. Hit stop. If you don't like it, reset it and give it another shot. Okay? However, I urge you to not, don't go too hard. You know, don't have the things flying into the book because you could break your IO lab. So just give it a nice gentle push. Again, we want to choose the region that we care about is here. First of all, go around your impulse. So it looks like it's about there. Get the mean value, the change of time, get your standard deviation, make sure you note your hertz. Choose the velocity before the collision, mean velocity, delta t, standard deviation, hertz. Remember that the initial velocity will be negative and your duration after for about a second, delta t, mu, which is your mean, standard deviation, and your hertz. I would actually probably go about a second, but all good, okay? Once you have that, this run's done. And our final run, we're going to use these coins in this bag. I would kind of wrap them up. What's nice is you can set them naturally in the USB slot. Just make them so that they're not going to fall off while you push this thing, that it's not going to somehow mess up because of the bag. You know, just be careful with that. Hit record, give it a nice gentle push, stop it. Again, zoom, double click. What I would even do is maybe grab the region that you care about. First up, make sure you capture your impulse, standard deviation, delta t, mean, hertz, the velocity before, mean, delta t, standard deviation, hertz, and the velocity after collision. About a second for each. That's not quite a second, but around a second for each. Get some good data, and you're all good. You've now collected all the data you need to collect to finish this lab. What we're doing on this lab is we're going to use the impulse and the velocity change to figure out what the mass of our cart is. Further, we're going to see the effect of adding more mass on the impulse and on the momentum change. So hopefully we'll learn something from this, and good luck.